Right. Hello, everyone. I'm James. I'm just going to talk about what I've been doing, you know, over the last few years. So two things I want to talk about is this language implementation I'm doing. I've actually written a whole bunch of different language implementations. I can't decide what I want to do, but I keep coming back to this one, which I kind of like. So I've just sort of decided to stay with it. And then I'll talk about code generation for synth definitions, which is a separate library, but it's in this, there's bindings in this language to it. So you can programming synth devs in this language. So the buzzwords of this language is it's dynamically typed, interpreted, mostly functional, object-oriented with linearized multiple inheritance, which is something from like close in the Dylan programming language. Multiple argument dispatch, immutable, fully persistent data types, thread-safe mutable data, pervasive auto mapping like APL, a concurrent runtime, and it's reference counted. And you can use emojis for your identifiers or Unicode in general. Okay, so there's some issues with SuperCollider, at least in my estimation. You can't dynamically add classes and methods without recompiling your class library. There's no namespacing for classes. The interpreter is single threaded, so it's not really running, concurrently. It's really easy to introduce garbage collector bugs in primitives if you forget to put a write barrier in where there should be one. So you can, and the problem with having a garbage collector bug is that it manifests somewhere way after the actual place where the mistake was happened. So they're very hard to track down. And in SuperCollider, all the math is done with double dispatch for binary operators, so that and just in a single dispatch language, double dispatch is kind of a clunky thing. So I'm gonna sort of handle these one by one and how I address them in this language that I've been working on. So first is adding classes and methods. So in this new language, which this is sort of what it looks like, here this is just an expression. It's not a declaration. So I'm creating a new class called shape, which is a subclass of item, which object has only three subclasses in this language, and you have to inherit one of them. So you can do this anywhere in your code is create a new class. And in this case, shape means the shape of a matrix, because that's what this the way the synthesizer works is everything's matrices. So here I just define a constant at the top level. Def means you're defining something at the top level. So I define a scalar shape. And I'm creating an instance of the shape class and giving it fields that are rows and columns, each being one. The classes are just type tags, really. There's no instance variables required if you have a certain class. It's kind of unusual, but you can give whatever instance variables you want to in any instance of a class. So you want to add extra metadata to an instance of a class, you can do that just by adding more instance variables. You can do that dynamically. So this next is a implementation using multiple argument dispatch of a call method. So this is dynamically creating a method. So if you use an instance of shape, and I mean, not an instance, you've used the class shape, which is what shape underscore class means, not, it's the meta class of shape, basically. So if you use that as the function and you apply it to rows and columns, well, let me show this. So basically, call of shape and rows and columns is the same as applying shape to a tuple of rows and columns. So this is a call is the method that gets called if you apply something to something else. So this is a way to basically create a constructor. This language. I mean, maybe I could add some syntactic sugar so it looks prettier than this, but to declare a constructor. But that's how it works at the lowest level. Also, this function, this whole declaration of function call is that is a syntactic sugar itself for a defined method call. So you could call define method, give the method name and the argument types and the argument names and a lambda, or the argument types and a lambda, and that would define a new method. This syntax is a simpler way to do that. Here's another, basically the same method, except the rows are omitted. So you're just creating a row vector shape. And then here's how to just make an instance method. So the length of the matrix, which is the number of elements in it, is just the rows times the columns. And there's no this or self in this language, it's just another argument. All the arguments are equal, and methods are not in their classes because they have multiple arguments. So the second issue is there's no namespaces for classes, and that's solved with modules. So you can just import a module. If you import a module name stuff, then if you want to use a name within stuff, you do stuff dot some name. You can import a module and rename it as something else. So now you would do x dot name, so that would help you prevent a collision if you got something else called stuff in your in your code. You can just import everything from the stuff module directly into your namespace, which is kind of dangerous because you can have collisions that way. But whatever you import is going to overwrite whatever's there if there is something already there. But it can be useful if you want to use some domain-specific language and have everything just right into your namespace. You can import just some names from the module, or you can import names and rename them. So these two I'm going to take together, the single-threaded interpreter and basically the garbage collector in general. So the reason why language like SuperCollider is single-threaded, and also why Python has traditionally had a global interpreter lock, so basically protecting the interpreter from concurrent access, is because there's so much mutable state involved that can't be accessed concurrently. The class library has class variables, which are mutable state, and the garbage collector is a big piece of mutable state, and all the objects are mutable, so they can't be safely shared. And the rule of safe concurrency is do not share mutable state. You can have immutable state and share it, or you can have mutable state and not share it, which means keep it thread local. And or you can protect against concurrent access by using a mutex. So this language I have provides all three of these methods. So first, almost everything is immutable, and this comes from my experience with having written SAPF, which I don't know how many of you have seen SAPF, which is what I just released maybe a month ago or something, which is a little forth-like language where all the data types, except for these refs, are immutable. And so all the records, arrays, maps, tuples, lists, they're all immutable objects. And you modify them by creating a changed copy. Basically, you say, take this object and change this field of it, or merge it with this other object and give me a new one. And so you get a new changed copy. And there's a few objects that are mutable, and they're protected by mutex. So you can safely share them across threads. There's these ref classes. You can set a value, get a value, or update a value with a lambda. And that's protected by mutex. And I'm using basically the same implementation of immutable data structures that are in the closure language. I mean, it's not written in Java, but it's there's a library by a man named Juan Pedro Bolivar Fuente, and he's implemented this library in C++ that's it's very good. I really like it. That implements all these data structures. So a fully persistent, this is a definition from Claude, but it was better than what was in Wikipedia. So this is an AI definition, so I'm taking a grain of salt. But so a fully persistent data structure allows access to all previous versions after each modification, preserving the complete history of changes while creating new versions. And importantly, that they share structure with the older ones so that it minimizes memory usage. So if you change one field in a record, this record is represented as a tree structure. So only the little path on the way to that field will be new objects. So this data structure could be huge. I mean, it could be all your global variables, which is and so only a small amount will change. So each operation creates a new version without modifying existing versions. And that enables efficient time travel through the structure's entire evolution, which means that doing undo is just saving a pointer to the previous thing. So you just, and which, you know, if you don't lose the pointer to the thing you just modified, then that's your undo. Just go back to that. And that will share everything except the change. So it's also memory efficient. And since the objects are immutable, they can be safely shared across threads, and copying them is just as cheap as copying a pointer. The benefit that you get out of that is that if there's no mutation, that means you don't need garbage collector write barriers. And the other thing is that if you have a language without mutation and without laziness, like Haskell, then it's impossible to create a cycle because every new object has to be created from old objects. So old objects can't reference new objects. And the only way you can do that is with these mutable references. So, and in my experience using SAPF, you don't need mutable references very much. You can use them or there's also mutable queues and stacks. You can use them to communicate data to other threads, but in general, you're not going to be creating cycles of refs. It would be kind of unusual to have that happen. So, or at least currently, as far as my experience goes, maybe in the future that'll be something, but I think you can manage refs without having to worry about cycles. And so that means that reference counting is easy to make thread safe. You can use a smart pointer, and that's how all these values in this language are implemented, they're a little like in SuperCollider, this pi or slot piece of data that's either an integer or a float or a nil or bool, or it's a pointer to an object. And so in this language, if it's a pointer to an object, then it's a reference counted smart pointer. And so as long as you use this value object, it's always going to manage the objects safely for you, the reference counts of the objects. And so you don't have to worry about having a garbage collector. But in all my unit tests, I check how much data might have been leaked, and it's always zero, so which is good. The other thing about this language is there's no global variables. So the top level scope is thread local. And which sort of makes it like an actor's model language. I mean, in actor's model languages like Erlang, there's every actor only knows what it's the scope that it was started with and what it's been passed as values. And so the same thing happens with this language. So the top level scope is mutable, so you can share it, but it's maintained in a persistent dictionary. So it's exactly the same as one of these immutable objects, but it's able to be modified in place efficiently because there's something in Clojure called transients, but also in this C++ library called immer that I'm using. If you move the object into the modification, then it will do the operation in place. And since the thread local scope is not shared, you can safely do that. So it's mutable, yet it's a persistent data structure. And when you fork a thread, it just copies all your thread local data to the new thread, which is just a pointer copy. So everything is shared to the old state when you fork a new thread, and then that thread can go and efficiently modify it. Won't be as efficient as the first thread can still keep modifying its things in place, but the second thread will have to start doing a little more path copying, but it's not a problem. So then there's for references, if you have these mutable references, you can use those to have shared sort of black words of data, or just large, if you want to have large shared pieces of state, like the score of the piece or something like that, shared between multiple threads, you can do that using these refs. Just update these pieces of information. Those can be safely shared between threads. And then so we're going to talk about double dispatch, and that's solved because there's multi-methods, which means multiple argument dispatch. So to implement math operations in SuperCollider, you need to use double dispatch, and that means there's lots of implementations, things like float, perform binary on simple number, perform binary off on simple number, and similar methods like that. So these just make the logic sort of hard to follow, rather than just having one function and it takes a float and another float.
Okay.
And so classes don't contain their methods. Multi-methods are defined outside of any class. They just look like function declarations. And multi-method dispatch lets you have the dispatch logic catch some dynamic type errors earlier than you would have caught them in single dispatch. Because if you pass one of the following arguments in single dispatch and it's a wrong type that won't work in that context, then you'll find out somewhere later. that was wrong. It's still not static typing, but it's better than having types on your argument. So the other advantage is that functions that belong together aren't spread out over the class library. So if I have a little function called as signal, which needs to convert something to a signal, I can put them all in one place. So if it's already a signal, then I just return it. And if it's a real number, then I make a scalar signal out of it. If it's an array, then I make a row vector signal out of it. And yeah, so as I said before, so if you add type more than one argument, then you can check that type with using the method dispatcher. So here, for doing these function basic graph rewriting operations is what this code was for. If you have a plus operation and it takes two rewrite expressions, then it creates a new rewrite expression. It's got the add operation. It's basically a node in a rewrite tree, which is another topic. But and sometimes you want multiple implementations based on not the first argument, but on another argument. So as in the code generator, the real difference that happens when you're generating a UGen expression is that it's which unit generator you're generating is what determines what code gets generated. You could flip these arguments and just have each unit generator implement a method taking a code generator, but then if you're in a single dispatch language, then you're spreading out code generation all over all the classes. And maybe you're not, maybe you want a different code generator. So how did you want to, like, maybe there would be a Rust code generator. So I don't know. So then you'd have to put Rust methods in all your classes. So this lets you just have something that's parameterized on both the type of the code generator and the type of the UGen expression. So another thing that SAPF has, and well, SuperCollider has this as multi-channel expansion for unit generators, but in this language, it's for all methods, which is auto mapping. And so if a function expects a single item for its argument, but instead receives a sequence, which is like an array or a list, then the function is applied to every element of the array, and an array is returned for the sequence every. So it could be a lazy list. So if you so for a scalar like 9, if you do the square root of 9, you get 3, and then if you do the square root of a list, you get a list. That's and you only had to write square root for scalar. Like, so if you write square root method for a float, and then if you apply an array to it, this just happens automatically. You don't have to write a method for applying an array to square root. And it's based on this inheritance where you're either inheriting for concrete objects, you're either inheriting from item or you're inheriting from sequence. And the object class itself is sealed, so you have to inherit from one of these. Then there's another mix-in class that inherits from object, which is for things like the class numeric, which is not a concrete object. It just tags other types as a mix-in type. So yeah, so the other thing is that there's in SuperCollider you could do 9 dot square root or something like that. So in this language, you just get rid of the dot. So an argument can be moved out of a function. The first argument can be moved out of the function just by putting it in front. So the other thing is that this is also from SAPF, but SAPF also got it from a language called F-script, which was a language based on Objective-C, which had these at operators, and there's a paper called Object-Oriented Programming Array Languages, or something like that, OOPAL. And it proposed these at operators. And what that does is it forces auto mapping on an argument. So if you have a function or a constructor, like this is the array constructor, that takes it, that can take an array, but you want it not to take an array, you want it to actually iterate that array, then you can use this at operator and it will do that. So in the first instance here, it's saying, you know, this A at comma B, it expands the A and you get this first list at the bottom. And then the second line where A at comma B at, then expands both of them, and they're expanded in parallel. But then you can also do Cartesian sort of nesting of loops where at 1 is the top level loop and at 2 is the bottom level loop. So you can sort of do these tables where you have, you expand A in the outer loop and B in the inner loop, or in the second instance there, you can expand B in the outer loop and A in the inner loop just by putting at 1 and at 2 in the right place. So that lets you do, you can construct data using sort of the similar idea of multi-channel expansion, but you have control over how it works. Doing this means that you almost never have to write an explicit loop in the language. Like SMPF doesn't even really have loops. It's got a while, but you never need to use it. So next, how am I doing? So the next thing I'm going to do is talk about code generation, and so this, unlike SuperCollider, it's all signals are matrices, so unit generators. Well, there's no real unit generators. All signals are matrices, so everything that can flow down from one thing to another thing is a matrix, and it supports 32 and 64-bit integer and floating point signals, and it supports multi-rate, including like intermittent events like triggers or gated subgraphs, and delays are written as different equations. Like there's a let-rec mode in Faust that lets you do this, but it's just the way you do it in this language. So a lot of signal processing equations are difference equations, or also called recurrence relations. And there's no block diagram operators like in Faust. They're not really.
It's right there. It's right there. Yeah.
You can have auto mapping or algorithmic construction. Basically, you've got this really high level language to build graphs, just like you have in SuperCollider. So it's not like a small language like Faust. So graphs are created by calling functions that create nodes. The node types are either just a constant, or they're simple math operators, or they're delays. You can initialize a delay, read from it, write to it. There's IO operators, and there's control flow, like if, switch, and for, which these sort of allow you to make multi-rate things happen. Like an if or a switch, let you conditionally execute some subgraphs. And that gives you things like pause, which was a unit generator in SuperCollider version 2. You use like if, and things like that. So that's sort of one origin of multi-rate. graphs. You can't do this kind of thing in Faust. At least, I don't know, that they did do a paper on Faust where some of these things are gonna be implemented. I don't know if they've implemented them yet. And you also have matrix manipulation operations. So you can transpose a matrix or reverse it, things like that. Okay, so every signal has a type that's the three components. It's got a matrix shape, which is rows and columns, and it's got an element type of the four they're supported, and it's got a rate, which is either constant, which just means it's constant. Initialization time, so sample rate and sample duration are initialization time values, and anything that depends on them becomes only them and constants becomes an initialization time evaluated expression. There's reset, so you can reset a graph, and there's events, which are like setting control in a graph, and then there's audio rate. And this is sort of in a linear sequence. So you have in general, if you have an operator that takes multiple rate inputs, the output will be of the highest rate of the inputs in general, except for some of the control flow things, some other things that have slightly different behavior. So in the graph construction, when you're calling functions to build a graph, sort of there's four steps that are happening every time you're creating a new node in the graph. It does constant folding, which means that if you have an operation of constants, it just does that immediately, and you get the constant out, so you don't have to calculate the constant at audio rate. And it does rate inference, so that thing where it decides what the rate of the output is based on the inputs, it's done. And it does common subexpression elimination, so if it determines it uses a hash to do this, but the hash of the current expression is the same as a hash of an expression that's already been generated, then it will just replace what you're building with what's already been built that way. You don't have to worry about having, like if you call a function that's got a little subcalculation in it that's also going to be done by another instance of the function you're calling, that will be optimized away. And then it does an algebraic simplification of that expression by graph rewriting. And so there's a whole bunch of rules that apply to graphs, and they can be rewritten. And then when you rewrite the graph, it's going to create new nodes, and then they'll go through these four steps again. So it's sort of this iterative process of rewriting and doing the constant folding, the rate inference, and the common subexpression elimination until it's done. That's a terminating process, but that happens every time you create a new node. And then, so for the expression rewriting, there's a whole bunch of rules that are define math identities to simplify expressions. So like if you take the double negative of a value, it will just return that value. And the rules are pattern matched. So and the left-hand side replaces the right-hand side. There's 120 rules currently, or more than 120 rules currently. And I still need to write more. And so once you've built a graph, then there's a graph compiler, and it has a whole bunch of passes. And so the passes that it does are, first it merges delays. So if a delay has the same inputs and initialization as another delay, then it'll just make that into one delay. That can happen that can happen for a number of reasons. If you're calling different functions, they're each delaying the same input, and they'll be merged into one delay. Then it topologically sorts the graph so that every node, all its inputs preceded in the list. It calculates the delay lengths. Some of those delay lengths can be initialization time expressions. So they might not be just constant numbers. It does shape inference, so it figures out the sizes of all the matrices in the graph. And that can be a recursive process because when you read a delay, you don't know what the matrix dimensions of that delay are yet because you haven't gotten to the right. So it has to do this recursive shape inference to figure out what the dimensions of arrays are, especially in feedback loops. It does type inference. Then it cuts the graph into expression trees. So in order to write out a statement of code, you need to take the graph and turn it into trees. The other reason why you need to do that is cutting the graph helps you find all the places where you need instance variables or local variables in your code. So then you take the trees and you put them into loops. You find like a loop that's there's sort of an algorithm that for creating loops and figuring out which trees can go into them. Basically, that the loops have to preserve the topological order of the graph, and they have to be all expressions that are the same matrix dimensions. Then you separate the loops by rate for the 4 different rates that are calculated, and then you emit C++ code, compile it, link it, and load it. So I can show you what coding basically synth defs and unit generators looks like in this language. There's basically just a node creation library for this, and all the graph compilation and code generation is happening in the C++ library. It used to be written in this language before I changed everything to be immutable. I haven't just rewritten it after that. And I already had this C++ library around, so I just used it. So, but this is here now. So this is a little library that creates nodes. This is just sort of what it looks like. Signal expression is the root class of these operator nodes or expression nodes. And there's little constructors for them. So so this is what a synth-def would look like. This is the bubbles patch, this language. Sort of all written on one line. So I'll just read it right to left. That's what these bullet points are to describe. A 0.4 hertz low frequency sawtooth is multiplied times 24 semitones, and that's added to a sawtooth that takes that has sort of 2 inputs, so it's a stereo sawtooth wave that's at sort of beating frequency, and then that's multiplied times 3 semitones, and that gets added to 81 semitones, and then there's this piping operator, which allows me to take one expression and move it into the first argument of a following expression, even though the part to the left is of a lower precedence than function application. So this piping operator, which is also which I took from F#, and it also I think exists in some Mozilla versions of JavaScript. That just lets me pipe it into NN hertz, which is numbers to hertz, which is MIDI CPS SuperCollider. But I think Kima uses this name. It's shorter. I like it. So, and then that goes into the sine oscillator, which is multiplied times 0.04. C means centi, so it's just multiplying it times 0.04. It's very there's basically some scaling suffixes. Those are also in SAPF. So you can write 4C in SAPF, and it'll also say 0.04. And then that gets piped into a comb delay, and that goes to the outlet. So that's what a synth depth looks like, or a very simple one. So for a unit generator, the unit generators are just functions of language because there's no unit generators, built in. It's not like in SuperCollider, you're stringing together pre-compiled unit generators. In this language, you're compiling whole synth depths into one thing. So you can create functions that act as unit generators by writing code using the built-in sort of nodes, the very basic nodes. So this first example here is creating a one-pole filter, and it's got a signal input, which is X, and then A, which is the coefficient. You create a delay variable Y, and then you write to Y the result of the input plus the coefficient times a one sample delay of the output. That's a simple one pole filter. So it's basically feeding back the output. And then a 1-0 filter is you have a signal and a coefficient, and its output is the input plus A times a one sample delay of the input minus the input. And then there's a fade in. I guess I had separated these. There's a fade in unit generator, which takes a signal and a time, and then it calculates sort of a slope variable, which is 1 over the time times the sample rate. And then you create a delay variable Y, and you return, basically it's the minimum of 1, which is, you don't want the amplitude to go above 1. So you have the slope plus the previous value of the ramp. And you take the minimum of that 1, you write that back to the ramp, and then you cube it and multiply it times the input. So the cubing gives it, this sort of more tapered fade in. That's a fade in operator. So that's basically the language and the code generation. And for the code generation, there's a lot that remains to be done. Event code generation is not working yet. I know how to do it. It shouldn't be hard. There needs to be a scheduler. There's not yet a synth server protocol, and I had SIMD code generator working in a previous version. I have to rewrite it now because I've changed everything. So that's not working yet, or just hasn't been implemented. So related work, the multi-methods and multiple inheritance is very similar to Dylan. I'm using persistent data structures and the hash array map tries that I'm using for the data structures. Those were implemented in Clojure first. And for code generation, what I'm doing was actually inspired some years ago by reading the paper on Kronos, which is by, I don't know how to pronounce Finnish, Vesanori, which is multi-rate and reactive. I don't think it can do, I'm not sure if it can do things like pause, things like that. There's also ARF by Jakob Levin, which is multi-rate and has multi-dimensional signals. It's very interesting. I think I had an email conversation with them. It can't do like sort of demand-driven things. Like you can with this using control structures and things. All right. Well, if I have time, I can talk about the experiment. How am I doing? I got 6 minutes. Does anybody have questions? Yeah.
Just answer your order of operations the same way as right.
It's basically postfix, so it's just postfix. So you do arguments and then operators. Just a stream of. I mean, yeah. So in concatenative programming, which is SIPF, is not quite concatenative because it has a lexical environment, but every word is a function, even a constant is a function that takes the stack and returns the stack with the number on the stack. So that's just how it works. It just, you know. But this language that I just showed does have precedence. It's got lots of levels of precedence. So,
I have a question here. So the global interpretive plan and this that it does run currently, or can you do like through orientation where you run on each core?
yeah, you can create OS threads. Yeah. So yeah, so there's well, I guess there is a main thread that's when you start, but there's no interpreter thread because there's every thread is an interpreter thread. So and there's no global variable, so there's no global state really. So yeah. What else? Yeah. Let's do with I think that was what do you mean by pure? Oh, for the SAPF? Yeah, so yeah, with the formal thing behind. Oh, well, so SAPF is inspired by a language called Joy, which was by a person named Manfred Bonkton. Yeah, I don't. Well, so it's so it's and the reason why I called it sound is pure form, I just had this feeling of when you operate on signals and you get a signal and it's a lazy value, it's not this mutable thing, or it's this abstract thing, you've got samples coming out right there. It just had a different feel for me, a way of programming it, or programming with values. So it's like and these values are pure, they're functionally immutable. So generating things at the end, there's a little function at the end that's hidden from you that's generating all the samples. That's but it's mutable, but it's also protected by spin lock, so you can't multiple threads can't damage it. But yeah, pure form seemed like they're pure functional things, and you're creating them functionally. So it just seemed like that's where the name came from.
One is what.
No, I don't. Yeah.
You seem to be and my question, are you sort of
How do we try to draw towards the language you want to
use or the actual
writing like
stuff like
There's a joke that goes like something like, you know, I was using samples and I thought that was cheating, so I started, you know, recording real drums, and I thought that was cheating, so I learned how to play drums, and then I thought that was cheating, so I started making my own drums, and I thought that was cheating, so I started raising goats to make the goat skins to put on my drums, and then now I don't make too much music anymore because all the goat farming. But yeah, it started with C sound. Like I learned C sound and I didn't like it because it was assembly language kind of. And of course now I see why that's brilliant. But I wanted to be able to write algebraic expressions and create things, so I made this language called symptomatic, and yeah, so yeah, I've always been dissatisfied with a level of expression if I can think of something better, so that's why I have serial audio programming language developers. All right.